So we're starting out with a theorem called the extreme value theorem. And this theorem says if f of x is continuous, on a closed interval AB, then f has an absolute max and an absolute min on the interval AB. If f of x is continuous on a closed interval, then f has an absolute max and an absolute min. Okay, so you might remember yesterday we had a couple of graphs, example 1 and example 2, that didn't have absolute maxes. Remember, the first one had the point at the top with the open hole, and then the second one was just a straight line that had the hole at the top. So it's not guaranteed that a graph will have an absolute max, and it's also not guaranteed that a graph will have an absolute min. Some don't. But if the function is continuous on a closed interval, then it's guaranteed to have an absolute max and an absolute min. That's all this theorem's saying. So some functions don't have absolute maxes and absolute mins, but these do for sure. All right, so yesterday we just found the absolute maxes and the absolute mins using just looking at the graph, graphing it on the calculator, or actually having a graph already. So today we're going to find the absolute max and the absolute min without a calculator. Okay, so this is the method for finding absolute maxes and absolute mins without a calculator. So yesterday we just looked. Now today we're going to not look at the graph and still find it. Okay, but since it's only guaranteed to have an absolute max and an absolute min, when you have a continuous function on a closed interval, the method I'm about to show you only works for continuous functions on a closed interval. And because of that, it's called the closed interval method. So the method today that we're learning only works for continuous functions on a closed interval. You might be able to find absolute maxes and absolute mins for other functions, and we'll learn later how to do that. But for now, we're just focusing on these types of functions that are continuous on a closed interval. And again, because that's the case, it's called the closed interval method. And by closed, I mean that there's brackets. If there were parentheses, then it's called an open interval. All right, so this is just a three-step process. The first step is to find the critical values. What were critical values again? Where f prime is 0 or undefined. Good. So all the places where the derivative is 0 or where the derivative is undefined. So find all those places. And remember yesterday we said those were important because extreme values might occur there. So that's happening here. The extreme value might occur there. That's why we're finding it. Okay, then the second step is to find the endpoints. Because it also might be the case that the absolute min or max is at the endpoint. Classic example would be just a straight line. Here, the absolute min is on the endpoint, and the absolute max is on the endpoint. So that's why this step is necessary, because the min and the max might be there. Now, if we were looking for locals, we wouldn't look at the endpoints, right? Because locals can't be endpoints, or endpoints can't be locals. But since we're looking for absolutes, the endpoints might be. Okay, and then the third step is plug all these values into f of x. And then the biggest answer you get is the absolute max, and the smallest answer you get is the absolute min. All right, so let's try that. Our first function is going to be f of x equals x to the 2/3, and it's on the interval -2, 3. And we're going to find the absolute extrema. Just to remind you on the vocabulary, what's the other word for absolute? Global. So I could have said find the global extrema. It would have been the same question. All right, so first step is to find the critical values. That's when the derivative is 0 or undefined.
At this time, will the rest of the sophomores go into redo day? Please go to the back of where the bus lot is. Your buses are ready.
So Kyo through. Okay, so then to find the critical values, obviously you need the derivative, right? Because the derivative is where the critical values are where the derivative is 0 or undefined. So I'm taking the derivative. So that's 2/3 x to the -1/3. So then I need to set this equal to 0, and then also set it equal to undefined. And while I'm doing that, I'm going to rewrite it. The 3 is obviously on the bottom because it's 2/3. And then the x to the -1/3 I could put on the bottom and make it +1/3. So that's what a negative power means. So there's the derivative, and we're going to set that equal to 0 and also equal to undefined. So we're in step 1 here, we're looking for the critical values. All right, so when is a fraction equal to 0? When the top is 0, right? A fraction is going to be 0 when the top is 0, because 0 divided by something would come out to 0. Well, this top can never be 0, because it's 2. So this fraction can never be 0. So there's no critical values occurring from the derivative being 0. Okay, on the other hand, when is a fraction undefined? When the bottom is 0, right? So setting this equal to undefined is the same thing as setting the bottom of it equal to 0. So 3x to the 1/3 equals 0. And then you can just divide the 3. And then this is just for other problems, you can see what the answer is here, but how do you get rid of cube root? Like this is the cube root, right? So to get rid of cube root, you would cube both sides. So that would just give you 0. Okay, so we've got one critical value. The critical value is x equals 0. And that's where the derivative is undefined. There could be 2 or 3. There could be a couple from here, one from here. But in this case, there's just one critical value. Okay, so step one yielded one number, x equals 0. Okay, now step two is very difficult. Finding the endpoints. I'm being sarcastic. It's really easy, right? It's -2 and 3. It's given in the interval. Okay, so check. We're down to step two. We just found it. Okay, then for step three, you take all those values and plug them into f of x. So I've got -2 and 0 and 3. I'm just going to make a table of those. So really what's happening is this method is saving us a lot of time. There are infinitely many numbers in between -2 and 3. And so if we had to find the absolute max without some method like this, we'd have to try every one of them into the function and then see which one was the biggest one. Because the absolute max is the biggest y value. So theoretically, I would have to try every x value and figure out every y value to get the biggest y value. But what this method is telling us is you don't have to try every number because it's either going to happen at a critical value or an endpoint. So it doesn't matter for the other ones. They're not going to be the absolute max or min. So that this is a big time saver. There's just 3 numbers to try. It's got to be one of those that's the highest point, and one of those is the lowest point. All right, so for -2, plugging it into f of x. So if I square -2, that's 4. And then the cube root of 4, I don't know what that is, and I'm trying to do non-calculator. So I'll just write down the cube root of 4. So again, how I got that is I took -2 and squared it, and that's 4. And then the 3 on the bottom of the fraction means cube root. Okay, then for 0, obviously 0 squared is 0, and then the cube root of 0 is 0. So the answer for 0 is 0. And then for 3, 3 squared is 9, and then the cube root of 9. So then which one of these is the lowest? 0 is the lowest output. So the absolute min occurs at 0, and the value is 0. So the output is the minimum value. The value is the y value. Okay, and then we don't know what these numbers are, but we do know that this is bigger than that, right? If you take the cube root of 9, that's going to be larger than the cube root of 4. So the absolute max happens at 3, and the max is the cube root of 9. I changed the wording, it says the same thing, just so you get used to different wording. Okay, so this closed interval method is the non-calculator way to find absolute maxes and absolute mins. But it only works on a continuous closed interval. continuous function on a closed interval. So we're going to try another one here. This one's f of x equals the cosine of x plus pi over 8. And it's on the interval 0 to pi. Okay, so cosine is a continuous function because it's connected, and we have a closed interval. So since we have a continuous function on a closed interval, we can use the method that we're learning today to find the absolute max and the absolute min. So the first step is to find the critical values. Critical values are where the derivative is 0 or undefined. So I'm going to need the derivative. Derivative of cosine is negative sine. And then there is kind of a mess in there, but the derivative of the mess is 1. So if I did chain rule, I would just times by 1. So it's not super necessary to write that down. So here's the derivative. So now I need to set this equal to 0 and equal to undefined, because that's what a critical value is. So sine is a continuous function. So that means it's never going to be undefined. If you look at the graph of sine, it's connected. It's not undefined anywhere. So this time, the undefined part never happens. All right, so over here, we're going to divide by -1 first. So that's just 0 divided by -1 is just 0. And we're trying to do non-calculator. So we've got to think about when the sign of something is 0. So we'll look at the unit circle for that. So the sign is the y value. This is the point 1, 0. And this is the point -1, 0. So the sign is 0 at these two locations. But there's a lot of names for these locations. This is called 0 and 2 pi and 4 pi and 6 pi, etc., etc., etc. It's also called -2 pi. And this is called pi and 3 pi and 5 pi and -pi. Okay, so I'm just going to list down some of these. -pi, 0, pi, 2 pi, 3 pi, etc. So some people, more than just you, I think, some people are thinking, why am I writing down this? Because it doesn't fall in my interval, right? The reason why is I don't have the final answer yet. This is an interval that the final answer needs to fall into. And so far, I'm just trying to figure out what this is. So I don't think about that ahead of time. I just write down a bunch of answers, and then I worry about this at the end. Because the sign of this number is 0. So that means if x plus pi over 8 is negative pi, then we'd be, because if this whole mess is negative pi, then it would come out to 0. Not if the x is negative pi. This is the hardest thing today so far. Is everybody okay with this? Okay, so I have figured out what this mess could be. This mess could be any of these numbers. And now I need to subtract pi over 8 from all of them to see which ones actually work in this interval. Because initially you might have thought 0 was a good answer, but I'm about to subtract pi over 8 from it, so it's not a good answer. All right, so that's, well, that one's negative pi over 8. These other ones are a little trickier to subtract pi over 8 from. Let's see, this would be, well, let's do this one. Pi is 8 pi over 8. So if I subtract pi over 8 from it, it's 7 pi over 8. And 2 pi is 16 pi over 8. So if I subtract pi over 8 from it, it's 15 pi over 8. Three pi is 24 pi over 8, minus pi over 8 is 23 pi over 8. And then negative pi over 8 is negative 8 pi over 8, minus 1 is negative 9 pi over 8. Everybody's still doing okay. Yeah.
So those values right there are the values like that you need to have in that interval?
Yes, and they're also all the possible x's that would make this be 0. For example, if I plug negative 9.8 pi over 8 in there, then I add pi over 8 to it, I get negative 8 pi over 8, which is negative pi, and then the sign of negative pi is 0. Okay, so now, since we have our final x value, we can see which ones we should throw out, which ones don't fall in the interval, because these are where the possible x's should be. So now the negatives are out. So just to re-emphasize, Connor, you might have kept this one, but it turns out that we needed to throw that one out. So that's why I wait till the end to worry about the interval. But it was a great question. I know a lot of people had that in their head. So, okay, and then this, let's see, which one's too big? This is less than 16 pi over 8. So it's good, because 2 pi is 16 pi over 8. But this one is more than 16 pi over 8, so it's out. So here's our two answers, 7 pi over 8 and 15 pi over 8. Those are our two critical values. Okay, then what was the second step? Find the endpoints, so much easier, 0 and 2 pi. So then you take all those values and you list them in a table. 0, 7 pi over 8, 15 pi over 8, and 2 pi. So I'll plug this one in first. 7 pi over 8 plus pi over 8 is 8 pi over 8, which is pi. So I'm taking the cosine of pi. So x value negative 1. Cosine is the x on the unit circle. Then for 15 pi over 8, 15 pi over 8 plus 1 pi over 8 is 16 pi over 8. That's 2 pi. So I'm taking the cosine of 2 pi. So 2 pi is all the way around to here. Cosine is the x value, so the cosine is 1. Okay, now I was trying very hard to make this a non-calculator problem. However, if I add 0 plus pi over 8, I get pi over 8. And pi over 8 angle doesn't appear on the unit circle. So we're just going to take the cosine of pi over 8 with our calculator. Comes out to 0.92. And then for 2 pi, that's 16 pi over 8 plus pi over 8, so that's 17 pi over 8. 17 pi over 8 doesn't appear on the unit circle either, so we'll take the cosine of that. It comes out to 0.92 as well, which we should have known because 0 is the same angle as 2 pi. So that was silly to redo it. Okay, so where's the absolute max? Right there, right? That's the biggest number, 1. So it's at 15 pi over 8. So the absolute max is 1, and it occurs at x equals 15 pi over 8. And the absolute min occurs at x equals 7 pi over 8, and the value is negative 1. Okay, so trig is tricky. Any questions on that stuff? Okay, got one more problem here. So for example 3, we're going to have a piecewise function. We've got f of x equals 5 minus 2x squared, and on when x is less than or equal to 1, and then x plus 2 when x is bigger than 1. Okay, so formula for f prime. First of all, why would I want a formula for f prime? To try to find the critical values, right? Because the critical values would be where the slope is 0 and undefined. So if I have a formula for the slope, that's the context we're in. Or if I just wanted to know the slope of this graph, then f prime would help with that as well. Okay, so the way piecewise graphs work is, we've talked about this some, but it's tricky. You can just take the derivative of this formula, and you can just take the derivative of this formula. But it's not quite that easy. But anyway, let's do that. So this would be 0 minus 4x. So the derivative of the top one is negative 4x. and the derivative of the bottom one is 1. And the tricky part is that doesn't work at the break. So the break between these two functions is at 1. So far, this is what we have. So the quick shortcut works most of the time, but it doesn't work at 1. It seems like this equal sign should carry down, but it doesn't necessarily. It might. We're about to find out if it does. But on some problems it does, and on some problems it doesn't. So you can't just assume that you're going to carry that down. That throws people off. They generally just write that down, and then they say they're done. Okay, so the quick shortcut does not work at the break. So we have to do the derivative the old long way at the break. So that is the limit, as x approaches 1, of f of x minus f of 1 all over x minus 1. And because f of x has two different formulas, we have to split this limit into two different limits. So we're going to take the limit from the right side, and we are also going to take the limit from the left side. Okay, so if the x's are bigger than 1, like 1.1, that's what's going on here, then we want to pick the bottom formula for f of x. So that's x plus 2. And if the x's are smaller than 1, like 0.9, then we want to pick the top formula for f of x. X minus 1 is in the bottom in both cases. Okay, here's the second hardest thing from today. The hardest thing was over there with that trig function. Went right at this moment when I was taking the sign of that and wrote this down. Second hardest moment is right here. This number is f of 1. So I'm plugging in 1. So which formula do I use? The top formula. So just to emphasize that, let's put this down. Because if I put a 3 down, you might think that I used the bottom formula, right? Because of 3, coincidentally, the bottom also outputs 3. I feel confident putting a 3 there because no one's going to use the bottom formula here accidentally. But someone might accidentally use the bottom formula here because we used the bottom formula there. Okay. So let's see, x plus 2 minus 3 is x minus 1. So that's convenient, the x minus 1's cancel. And so we're taking the limit of 1. And the limit of 1 is 1. Then over here we've got 2 minus 2x squared over x minus 1. took 5 minus 3 and got that 2. Then I can factor out the 2. Then this is the difference of 2 squares. So it factors into 1 minus x, 1 plus x. And then this is pretty close to that, right? This is 1 minus x, that's x minus 1. So if I factor a negative 1 out of that, I'll be able to cancel it. Actually, put 1 plus x in your notes because this didn't change. And then that's nice, the x minus 1's cancel. I'm running out of space here. So it's the limit of negative 2 times 1 plus x. The negative side, yeah. Then you can distribute the limit of 2. Just doing limit laws now. And limit of 1 is 1. Limit of x is 1. That's negative 2. I don't know why I wrote down the limit. You're good enough with the limit laws now. So that limit is negative 4. So we got different things from different sides, right? So that means the limit doesn't exist. And the limit we're taking is this limit. So that limit doesn't exist. And what's the special name for this limit? F prime, right, at 1. So that means f prime at 1 does not exist. So that's why we would have been wrong to include this line under here. Because if we had put a line under there, we would have been saying that f prime did exist at 1. That it was negative 4. And it's not. It does not exist. And usually what we do is we just leave it out. And that tells the person that it doesn't exist there. You could write down x equals 1 does not exist, but the math community doesn't usually do that. They just leave it blank and then assume that since it's blank, it doesn't exist. But there are times when you would do this process and you would get an answer for the derivative. And so then maybe you can transfer down the line. So you have to test what's going on at the cutoff, at the break, for a piecewise function. Everybody doing okay? Yeah.
So if there was a derivative at f prime of 1, would you the line underneath both?
Well, maybe not both. Maybe the one that, like, let's say, for example, it didn't, but let's say, for example, this had come out to negative 4. then we would have wanted a line under here, because this is the function that outputs -4. But it's also possible that, well, I'm pretty sure that if there is a line, it's gonna go with the one that, I'm not prepared to say that that is an absolute. I think I might be able to cook up some special example where the line went here. I'll have to contemplate that. But I don't, my gut tells me that's not gonna happen. Or if I could make it happen, it'd be some bizarre example.